Welcome everyone. We are very happy for this good turnout here in the Liszt-instituutti. Welcome to the Night of Science, and I welcome our lecturer today, Vizi from the University of Szeged from Hungary. And I'm not going to talk about what he's going to talk about because all I want to know is, will AI attack us? So please.
Okay, so welcome everybody. The answer is maybe. So shall I close the presentation now, or or shall I continue? So again, welcome everybody. My name is Zsolt Vizi. I'm from Hungary, from Szeged. I'm an assistant professor there, and also I'm working in a national laboratory concerning health security. And there I'm working on data-related and data-driven problems. So that's the reason why I'm here. And also I'm CEO of a company where we have software development projects and also AI-related projects. So I have some experience, but I'm quite young, maybe. So I try to share my experience in this topic with you. And this won't be a lecture. So I try to not to do a lecture because that won't be so, I don't know, exciteful for you, maybe. I'm a mathematician additionally, so just for your information, I'm a really dangerous species. I'm a mathematician. So what I have today is a science promoting talk, more or less. The title is really catchy. So from prompt to proof, measuring real AI intelligence. The idea behind this presentation is what I want to reach at the end of the presentation. If somebody is not familiar with machine learning and artificial intelligence and this kind of scientific stuff, so the background itself. So what I want to reach is to be skeptic. This is not a new, how to say, a big surprise, but to be skeptic, we need some tools, we need some approaches, we need some concerns, which we have to have in our pocket. And when a new AI wave is coming, then we have this in our pocket, and we can just evaluate all the new trends and everything based on this one. So that's my goal for today. So let's start with the most popular AI tool today, which is ChatGPT. So I want to tell a little bit about my relationship with ChatGPT. So he is not my friend, or she, I don't care. So ChatGPT is not really my friend, but we are working together in not in science and not in the research mostly, but one of my major hobby is TTRPG, so tabletop role-play gaming. I'm a dungeon master or a game master mostly, and what I use for the ChatGPT when I'm writing a story or when I'm working on a story which is already written in some book and there are some gaps, then ChatGPT could be really good tool for me to generate some content for that. Because how I see ChatGPT right now is that connecting those kind of textual information, which maybe I could do, maybe I could not, but generating a lot of text, which could be really inspiring for me. And maybe I can just pick some of the pieces and putting them together and creating a new one. But more or less, it's really inspiring sometimes to talk a little bit about how to build a word or do this kind of activities. And it's really good also, so you could also notice that for mass content, so like saying that, okay, could you recommend me something? And all the time, they can do 3, 5, 10 pieces of information or recommendations, and a lot of things can be done. And for this kind of mass contents, like when I'm doing this kind of job, the game mastering, then what the monsters are saying, then these are, you know, it's good to have it during the game. If not, then it's not a catastrophe, but having it, it's really nice. This kind of mass content is really good for me. Also, I did some deep research or deep search with ChatGPT, which is not that bad, but I cannot say that I operatively work a lot with ChatGPT in my work. So my work is mostly about research and some development and methodology research, let's say. But other people use this ChatGPT in another way. So, for example, Kim Kardashian uses ChatGPT for her exams. And she was not so, how to say, happy that she failed during the exams. And she said that ChatGPT was wrong all the time, which could be true. Naturally, because not all the, so this is about law studies, so legal studies, and ChatGPT couldn't answer all the questions in a really good way or a really precise way. But the problem is with this story is that, which is a widespread phenomenon, is that Lady Kardashian really believed without checking or without any control about the answer from ChatGPT, which could be really, really bad. But for her, it's like, it's cost some money. It's not a huge catastrophe. It's not really something which can go wrong. It costs some money because that exam should be retaken, but this didn't cost a life or something like that. But it happened, unfortunately, that it costed a life when a teenager talked with ChatGPT about some drugs, so about some medicines, that what should be the doses which he should use. Okay, so behind the story, this teenager guy was really addicted to these kind of drugs and medicines, which is also not a good starting point for talking with ChatGPT. But when he died, they detected that there was a conversation with ChatGPT where this dose recommendation was present in that chat, and the guy used that dose recommendation, which is really, really bad. And as I was reading, so this is from this year, so beginning of January, the sales spoken person said that so you cannot rely on ChatGPT in these kind of questions. So there's zero responsibility or zero, how to say, confidence ChatGPT has that it is good. So the answer could be good. So we should be skeptical of what ChatGPT gives. And this is, again, not a big surprise. But when we have this information that we are skeptical about what ChatGPT does, then the next question arises, then how to check that what ChatGPT can do. In which topics it is reliable and in which topics it isn't reliable, or at all AI, how to work with that kind of reliability and how certain we can be in a specific task that an AI-driven tool like ChatGPT. So behind, we have the GPT engine, and based on the GPT engine, we have the chatbot functionality, but this can be applied in any kind of area. So based on ChatGPT, for example, there are time series forecasting tools. That one is called Time GPT, which is good for forecasting time series. Forecasting time series means that predicting to the future, some points in the future, and having some information what will happen. It could be really useful, not for only just for the bank sector, but it's really important for the hydrology guys, for example, so for water management, because they are really rely on the information, what will be the water level, what will be the water flows, and so on. So I'm not against AI because I'm working with it, so I'm working on it. So I totally believe that we should work and we should live with AI, but as a mathematician, my question was all the time when I was working in the industry. After my PhD, I started working on driver assistance systems at a company, at a car, technically a manufacturer company. And all the time my question was why it is working, how reliable and how surely I know that this is really working, and how to measure that one. So that will be the idea of this presentation. But before that, maybe it makes sense to recap a little bit the background about machine learning and AI and data science and these kind of things. So we have many buzzwords today. So my experience, because as a mathematician, semi-informatician, I can say, I'm working with people who are not from this domain. And they, just throwing on you many words about artificial intelligence and clustering and regression and so. And yeah, after some time, I realized that they don't know what they are talking about. They just know the word, they just know as a buzzword, but they don't really know how to use it. They don't know the precise details. And I don't want to give you an overview or explaining all the words here, but for me, for example, these are the words which are typically thrown at me, and I have to just, how to say, put myself together and just think ahead that, okay, what that guy taught when they throw that word on me, and how to understand it, and how to maybe correct it, how to teach it, how to understand these kind of words. So classification and GPT and artificial intelligence and big data. What is the difference between big data and data science? What is a neural network? Is it an algorithm? Is it an area? What's the relationship with deep learning? And these kind of stuff you can meet also in any kind of articles, I can say, which is on a blog or Facebook or somewhere else. So my first, how to say, explaining or the explanatory picture is that, which I really like, that artificial intelligence is a really broad field, really, really broad one. So not only just the data-driven algorithms are part of it. My first question, because before I go into the deep, that how many of you, so just raise your hand, learned about machine learning or data-driven algorithms at the university or anywhere else at the workplace? So just raise your hand. Okay, some of you. Okay, good. My other question is that how many of you, if I can do that nicely, is familiar with this site? This is Finnish. So this is really, really, this is from Helsinki. So this is something which I shouldn't know necessarily. So I don't know, maybe there are some people who know the story behind these elements of AI and this AI challenge, which you did here in Finland. But I know that we totally copied and translated it in Hungary. So we didn't change it. So we didn't do any change because it was so nice and it was so elaborated and it was so well done that we just translated it. And we said to the people in Hungary that if we can reach 100,000 people with these elements of AI course, then some of them could win a PlayStation or something. So we tried to, gamify a little bit this one in Hungary. But all in all, I checked it also in Hungarian and also in this site. What kind of topics are concerned here, and many of them are also included in my presentation. And also here, I didn't get it from this one, but if somebody didn't do that and didn't learn about AI or machine learning, then I can recommend really much for you this Finnish Helsinki-related elements of AI course, because this is really nice and it looks really, really nice. So, so I think half or sort of the audience can learn something from my presentation. That's good. That's a good efficiency rate, I think. So artificial intelligence is a really broad field. So, for example, from that course, you can learn about that before this data-driven world and everywhere data was created. Artificial intelligence was used for really programming algorithms for robots. So for robotics, working with these kind of automated algorithms and how to do the automation and how to program bots for games, for example. This was in the field of artificial intelligence. This is really related in mathematics and computer science, so it could be really deep. But at the end of the day, many algorithms are really used also in the modern age. So in game development and in many other areas, and also in machine learning and deep learning, where really the data-driven stuff happens, many of the developments are inspired by the classical artificial intelligence algorithms. So that's why it's good to know the basics and the classical algorithms sometimes, because that can lead to a breakthrough. Machine learning is about we have data, and if we have the data, we can learn some specific tasks. And I will talk a little bit about these specific tasks, but how we can imagine them. But all in all, machine learning is really about, based on the data and based on the data input, I want to execute a task, and I want to get answer for a specific task. Deep learning is a part of the machine learning algorithms. They are based on the so-called neural networks. Those are the algorithms which are totally data-driven. So in machine learning, many statistical and mathematical and computer science related ideas are present. So the algorithms themselves are developed on a basis of statistics and probability and so on. But in deep learning, we don't have that one. So like we have Lego bricks and put them together and having a castle, but we don't know anything about how that castle is working. Really, we have just the bricks, and the bricks are in a self-alone way are understandable, but how we put them together, it's sometimes really tricky to understand them. And that's why the evaluation and understanding how the algorithms are thinking could be really, really difficult. So if you talk about machine learning, okay, yeah, what I missed is the data science. So data science is really something which is intersecting with these areas. So artificial intelligence and machine learning and deep learning, but of course, data science is another field. So analyzing the data, getting insights from the data, visualizing the data, and having the specific visualization is a totally different topic. So it's not part of the artificial intelligence and machine learning world, but those serve really how, as humans, can get insight from the data we have. And it is really useful and really crucial at many areas of the industry. So if we talk about machine learning, we typically, there are many categorization approach. So this presentation is based on, and some of the pieces are present here. It's based on another presentation which I gave 2 months ago, I think, where I shown how we can categorize machine learning algorithms. And that's the biggest confusion, I think, among the people, that how to categorize, and supervised learning means regression and these kind of stuff. So so these are the result of one categorization. The supervised learning, unsupervised learning, and reinforcement learning. I will talk just a little bit about the supervised and unsupervised learning. So I say that when I talk about supervision, that's kind of the type of the problem. How can I formulate this problem, which at the end will I have an algorithm as a solution. How can I formulate it as a mathematical or statistical problem? So that's kind of the idea behind this supervision, having supervision or not. So supervised learning is typically about learning or approximating a mapping or a functional relationship. The functional relationship means that we have an input, we have an output, and we have a relationship between them. Somehow we can calculate from the input what the output is. Okay, so that's the functional relationship. In the case of supervised learning, we know the input, not only just during the learning, but during the evaluation too. We know the input and we know the output. So we have at least the two ends of this process, and the algorithm between tries to figure out that how to create that function, which will give for a specific input that kind of output which I want. So you can see that both of them are available. So what does this mean for the output? So since we have the output, then during the parameter search, because these algorithms are really parameter-based algorithms, so having many parameters in themselves. So we want to find the best parameterization for all these algorithms. They also say models. So the parametric models, the learning is and the training is that finding the best parameterization. For this kind of problems, we are lucky in some sense because we know what the output is, what should be the output. So when I find the parameterization, whatever, it can be found randomly, or I have an idea what the parameterization should be, then I can try how good this parameterization is. This is called this kind of measure. How I can test it? It's called the error or loss, or additionally they say cost. So all three of them are typically used. This kind of measures are comparing what the estimation is, so what my parameterization gives, and what the original value is, so what it should be. And I can compare these values, and this loss value or error value, based on the value of that, I can maybe find a better parameterization. There are algorithms which can help us in this kind of optimization problem. So this error and loss is, I would say, can be created in a really natural way. So if my output is continuous, continuous means that it can have many different values, and a lot of statistical measures can be calculated. So I can calculate naturally the mean of that output. In that case, we talk about a regression problem. If that output is discrete, discrete means that I cannot have a statistical measure or statistical value like mean, only just the mode. So the most frequent value can be calculated. In that case, we talk about classification. I will show you an example on what a regression and a classification problem can be. Regression is like estimating something which can have any kind of value, like a price of a house. It can be a value in a time series, for example, a water level value of water flow. It can be a risk value, which can be a value between 0 and 1. It can have any kind of value between the two values. The discrete output could be something which can be like category, like having a binary decision at the end. So having the medicine or not, or having a specific disease based on the patient's information, deciding about whether this disease is present in the body or not. So that's a binary decision, but it can be, the classification can be also much broader, like we have a picture and we have an image, and what kind of animal or what kind of object we have on that image. So that's also a classification problem. In the case of unsupervised learning, so how the supervision comes into the picture and what does it mean when we don't have the supervision? The supervision is come by this knowledge of the output. So if we don't know the output, but we do really want to do something, so we have this functional relationship still, but somehow that output is not available for us. In that case, we are talking about unsupervised learning. In this situation, we have to be much more trickier. How to measure the goodness or the badness of that specific parameterization which we are talking about. In general, I say that the goodness of the pattern which I'm looking for, because unsupervised learning is typically looking after patterns. So not a really specific question we have, but we have some broader, some more general question, and at the end we can interpret that kind of information. We can have a little bit more specific, but mostly in unsupervised learning, we are mining the patterns, or we want to recognize the patterns. That's also used. One example is a little bit more concrete than the other, is the group membership. So this is similar to the classification, but we don't know the class. So we don't know that that specific patient or that specific image which category it belongs to. We don't know that, but we want to have an idea that maybe in our data sets and in our data, we have some kind of relationship which can be named as a category or a group membership. So it corresponds to one group or the other. And this problem is called clustering. The other typical unsupervised learning problem is representing our data with less variables. So having a really big table with many columns and somehow try to reduce the number of the columns, because for a human, I don't know, 100 or 200 columns, it's not really understandable or interpretable, and it's not easy to handle. But if we are capable of reducing the number of columns or reducing somehow the information which is describing that specific object which we are looking for, then this is called dimensional reduction problem. So this can be also something. If somebody is familiar with the large language models, then the embedding, if that word is familiar to you, then embedding is something which is related to that one. Embedding has two jobs, I can say. One is that somehow representing the textual data, so like characters in a numerical way. So that's one job of the embedding. But the other is that try to have a compressed numerical representation. So not having so many numbers which are describing that textual information, but having as less as possible, because working with that algorithms is really memory heavy, and it can be really hard if we have really huge amount of information which correspond only just to one sentence or one paragraph of a text. So this representation and dimensional reduction is also something which we have to work with. So that was only just a small recap about, just to understand that what I mean performance, when I say performance, when I say evaluation, that what I have in my mind, that in machine learning, we have these kind of supervised learning and unsupervised learning, and we are talking about inputs and we are talking about outputs. So for ChatGPT, we are talking about inputs and outputs. Input is the prompt which we type to the chatbot, and the output is the text what we have from the ChatGPT. So that's also like input-output relationship. And somehow ChatGPT has an algorithm, has this functional relationship, which tries to figure out that for this input, what should be the output, what should be the text it should generate. I will show you two approaches for this kind of how to test and how to understand that the algorithm works well, the model works well, the AI tool works well. One is, after this recap, it's quite natural, which is called the performance. So what does performance mean? The how good the model output is. So we have seen earlier that if we have a supervised learning problem, we can measure this cost or loss or error value, which will be some kind of measure for the badness. So if that value is small, then we can say that it's not so bad, so it is good. Additionally, in machine learning problems, we have the so-called generalization ability. Generalization ability is related to, okay, we have some text or we have some data which we are working on when we are looking for the best parameterization, but we have data which was not seen earlier, which was not part of this optimization problem. And what we want, that at the end of the day, we have these new data and new data sets and new data points, then for that data, the algorithm is still working well. But in the parameter search, it was not present. So there's the generalization ability that it can generalize the knowledge, or the knowledge which the algorithm knows is general enough that new data points and new information and new situations can be handled properly, or properly enough. So if you go back to the supervised learning, the classical situation, so I show you only just the two most typical situations for supervised learning. One is the so-called Boston house data set. This was about estimating the price of a house. So like having the information that how many floors it has, what's the area of it, what is the location of that house, and many information which describes a house which is sold or is on sale, and try to figure out that what's a reasonable price for that house. This is a regression problem. We have inputs and we try to figure out something which is continuous, because the house price could be anything. So in euros, in dollars, in forints. In Hungary, we are working with forints. It can be many different values. The other really famous problem was in the beginning or the first decade of the 21st century, the so-called ImageNet problem or the ImageNet challenge, which was about having images and try to figure out in an automated way what we have on that image. So in these kind of images, these images were not that big, so like 227 times 227 or something like that, so not so many pixels. And all the pictures was about one object, and they had the really big millions of these images. And the idea was, and the challenge was about try to find an algorithm which can classify these images. We have many, many categories. So we had over thousands of categories. I don't remember precisely the number of categories, but we had thousands of categories. And having image processing algorithms which can classify at the end of the day that what we have on that specific image. And of course, it's much better if they have more options and having some odds or probability values that, okay, I say that, okay, for this image, what I see here, that looks like a dog. So I have an idea that this should be a dog, and my idea is like 97%. And additionally, it could be a fox, for example, and I have 2% of odds that this is a fox, and I have many other options with much less probability values. So at the end, I just pick the highest value from the probabilities or for that percentage, and I will just say that, okay, on that image, I see that kind of object or this animal in this case. So in this situation, talking about performance, it's not super complicated because we have the inputs, the algorithm runs, we have the output, we have the original value, so the so-called ground truth value, which we have from the word, and we know it, and we can compare them. When we are doing this parameter search, we are talking about loss values, but when this parameter search is done and we have the new values, then we can create many evaluation metrics. So this evaluation means that I try to figure out how well the model works, and I can have many approaches for that. So you can think about that this could be an accuracy value, so how accurately I can predict the price of the house. But I can also talk about some kind of, I have many houses and many data, and how the prediction is correlating with my actual values. So that could be another one. It's called the goodness of the fit. It's not accurate value, so it's not accuracy. It's about a different perspective. When I can have a very accurate model, but this goodness of fit is not so good, then at the end of the day, I think that my model is not the best. Okay, so evaluation can have many approaches. If more complex the problem, more complicated evaluation approaches could be figured out. Okay, so if I have a very complex task, like I have a task that for question answering, I want to evaluate how well the ChatGPT can answer my questions, that could be a really complicated task, because I can have ideas what should be in the answer, but in a sentence, I can rearrange the order of the words, or I can use a slightly different words, or I can use synonyms, and I can do a lot of things which cannot be strictly or easily handled. So in that case, this evaluation can have many approaches how to really do that, how well question answering algorithm is working. Okay, so this evaluation could be not only just simply how precisely I can do something. it can have many different aspects, and we have to cover that aspects to have a detailed and comprehensive idea about how good the algorithm is, how good the model is. Okay, so this was about supervised learning, but I brought another example which is more related to ChatGPT, which is a generative algorithm. Generative algorithm means that my task is not really strict in a way that, okay, I need a house price, and that's only just a number. For a generative algorithm, it's much broader what I want to have at the end. So my example is from image generation. I was working on bad weather condition images, and I was working on a component in a self-driving car project where our task was to detect when a sensor is not working well due to some reason. So it could be due to some weather conditions. So for example, snowing or having rain or having a fog. In that case, the camera sensors are not so reliable. But we have to detect in a self-driving car that if the camera says something, that we have an object in front of us and it says any kind of distance value, or we estimate the velocity of that object based on the camera, and we have a bad weather condition and the camera doesn't work super well, that in that case, we cannot rely too much on the camera sensor. We should focus more on other sensors, which are not that easily affected by snow or by rain. For example, radar sensors are working in different cases really well when the camera cannot. So our job was to detect when a sensor is not working well. That was a multi-sensor team. It was a part of the so-called perception. So we are perceiving the world around us, and our team we were working on this kind of detection for many sensors. And there was a research problem that, okay, these kind of bad weather conditions and this really not so nice weather conditions, for example, in Germany or Hungary, it cannot be measured so frequently. Okay, it's not the situation in Finland, I know, so having a snowy day, but in Germany, when I was working on this project, it was a kind of a difficulty to collect images from weather where we have a fog. But in that case, we have to train our algorithms and we have to parameterize our algorithm to detect the fog, detect the snow, and so on and so on. So the idea was that, okay, let's try to create a generator, an image generator, which can generate, for example, based on an image which doesn't have any fog, doesn't have any snow or anything, any bad weather condition. Can we do a layer on that, or can we generate an image from that where we have that bad weather condition? And in this case, because this is a image generation problem, these kind of classical evaluation techniques don't work, just because it's hard to evaluate that I have a generated image, how to say that it is a good foggy image or a not so good foggy image. Of course, there are many techniques or many metrics which we can use. So one is really related to accuracy, or for this problem, we can say quality. How good the quality of that specific image which we are working with. So for example, if I have another algorithm, so not the generator, but having another algorithm which can detect whether I have fog on an image or not, then how well that, and let's assume that algorithm which we use for this kind of testing is also good. It's another question. So it's a philosophical question, that how can I say that another AI algorithm or machine learning algorithm is evaluating my current machine learning algorithm. That's really a philosophical stuff. But let's say we have an algorithm which can say that we have a foggy image or not. So on this image, I see a foggy weather condition. So quality is when I put the images which I generated to that algorithm, the result is good. In the sense that, for example, for foggy images, in most of the cases, the algorithm will say that this is fog. And that means that, okay, this is a good quality algorithm. Also for this generator, when I say only just bad weather conditions, then I can talk about how diverse the output it can result, so or it can generate. So this kind of diversity, when in the beginning I considered only just rain, snow, and fog, then what I expect from the algorithm, then it can generate all of the bad weather conditions, how to say, with equal chance, or all of them are good enough. So that's why we see on the right for the diversity that the height of the comparable to each other. So I don't have that big, really high column for the quality for the fog. Here I have some kind of equality or equal chances that each of these weather conditions could be generated with an equal chance and with a good quality. So that's something which, okay, if I see something like a histogram or a bar plot like this, then I can say, okay, this algorithm is diverse enough. I've shown you these two metrics or two approaches because I wanted to show you that, okay, different perspectives should be considered when I evaluate a model and an AI tool. But also what they did, that how to, because if somebody is working in an industry where managers are working, or I have a manager here, of course I have only just very intellectual and smart managers here, but if you have ever worked with a manager, sometimes you can present many numbers and many charts, but at the end of the day, they want one number, or just one number, because that's the most interpretable, right? So having one number, if that's high enough, then it's good. If it's not high enough, then it's not okay. So for example, we can merge somehow or fuse somehow these two plots. And the idea was behind, which is called perception score, and try to compare how similar these two plots are. So if I have a quality plot and I have a diversity plot, how similar they are, and what I expect they shouldn't be so similar, because for the quality, I expect really high value on one column and really low value on the others. But for the diversity, I need that kind of uniqueness or that equality. So if that score gives a high value, so that score says that these two plots are really dissimilar to each other, then my algorithm is working. So that's one way how I can describe with one number the goodness of this image generator. Okay, but there are many other ideas also, but I wanted to show you that having different perspectives, but they can also fuse and they can merge together, having just only one score at the end of the day, which can be really understandable for the management. So that was the performance. So like quality, accuracy, this kind of diversity, goodness of fit. In many cases, we really want to have good performance and having that evaluation performance. But on the other way, I can also evaluate my algorithms in a different way. And this will be the part of the topic of explainability. Explainability means that I have an output from my algorithm, from my tool, from my model. But how did that model get that? That's the question of explainability. Can I have an explanation about why this is the value? Which were the input values, the feature values? Which columns were the most important when I calculated this output value? This could be something like an explanation. Or for ChatGPT, that's the reasoning part. Why the ChatGPT says this one. Okay, that could be also bullshit, so we have to be skeptic with the answer. But if you ask ChatGPT that please cite some blog post or scientific article or something, you hope that the result will be like an article which is really good and not the quite opposite is stated in that article, because I have seen that kind of phenomenon too. So explainability is how I can reason, how can I explain the working of that model? Because if I can explain that, okay, this is how it works, okay, I'm control free because I'm a human, of course, and I'm a mathematician additionally, ooh, that's really bad. So if I can explain how this model works, then I'm a little bit closer to believe that this model is working. Okay, having the performance, having the evaluation, and having these kind of measures is really nice. But if I can understand it, how it works, then I'm a little bit more suggestive. So what I brought to you today is two type of explainability, which are working today. One is the so-called feature importance. So if I have tabular data, so having these kind of columns and this kind of information, like for a patient, the height, the body weight, the blood pressure, and many kind of information from a blood test, and so on. So in that case, if I want to answer that whether this disease is present or not, or what is the risk of that disease, or should I apply this dose of medicine or not, and I know that based on the input, which were the most important columns, that's something nice, because I can say that, okay, based on these informations, which would be the information as a domain expert, that would be the input for me, that would be the most important for me. And if that's the same for the algorithm, then I'm a little bit more concerned. So, so one is the so-called feature importance, which is used a so-called random forest classification and random forest algorithm. So in that case, these kind of plots are expected. So arranging and ordering, which is the most important one, more important a feature, higher the value which I have from the importance. This is from a paper which was concerning flood susceptibility. I brought two topics, mostly three, I can say. So self-driving cars, because I was working in it, and I like this kind of technology, how it emerges, and so. Hydrology, because I'm working with hydrologist people, so water management people in Hungary, also locally in the local area of Szeged. We have a directorate and we are working on some forecasting and data-related problems. And also on a national level, I started collaborating with the people to work on water level and water flow and these kind of data-related problems. And the third one is because I'm working in a national laboratory for health security, so this kind of public health and medicine-related problems is also in my topic or on my side. So this is from a paper which considered flood susceptibility, so this kind of plots. And if I say that the drainage and the slope and the river features are the most important ones, the author said that, okay, these are really how their model is working and how they would suggest any kind of flood susceptibility in that case. Another really important idea is the so-called SHAP value. So this is the shapely value, interpretable value, SHAP value, which generates really similar plots. So what we can see that we can have negative values and positive values, and the data points are visualized here. And what we see that if from one data point we used more from that one or use less that one, that SHAP value is generated in that situation. So this is another technique if we have this kind of tabular data. So we have that feature. So feature here means a column in a tabular data. Okay, so maybe I didn't mention that, but feature is like an attribute. So something which describing a description value, a data which I collect. So like blood pressure, some body height, body weight, and so on. Those are the feature values. So if I have really interpretable and nameable feature values, like when I have a tabular data, then I can generate these plots. And if I'm a domain expert, I can take a look at these images for a specific algorithm. And if I say that the features which are important for me are also important for the algorithm, then I can be a little bit more safe with the idea that this algorithm is working well. That can be something additional to the accuracy and performance. Okay, so this is like, again, a different aspect. Explainability and performance could be applied together. Another example, which was naturally emerging when this ImageNet in the beginning of 2010 was really a hot topic, then they were working new type is I cannot say this is really new, but there was a new wave of algorithms, so-called convolutional algorithms for image processing. And so year by year, this ImageNet challenge was submitted. And from year to year, different models and different solutions came. And after a while, they wanted to understand whether we have really good accuracy. So really better than the human accuracy, sometimes recognizing what we have on the image, but how these algorithms, which are better than humans for detection and classification, how they are working. And in 2014, Tyler and Fergus investigated in a paper that what we can see or what could happen in the brain of these algorithms. So if I say layer on any kind of image, this is what I imagine. So this is one layer which we have here. So we have an image and this kind of so-called convolution algorithm, which is like a window, and inside that window, I do a calculation, and that will be part of a new image, so to say, a new table of numerical values. And what I do is that iteratively I do it again and again and again. So having, let's say, newer and newer images, but that images are not based on pixels in that sense, but based on some other information. So like what you see, the feature maps, we have one feature map, one column of feature map after the input, and another one and another one. So we can say that in this case, in the convolutional part, so let's say the brain part or the extracting part of this algorithm, we have 3 layers. So when I say layer 1, layer 2, layer 3, then layer 1 is what is immediately after the input, so that kind of images. So what they have seen, and let's say that for the future is kind of a hope that it's still true, that in the first layer, the algorithm starts learning that where these kind of gradients are, which are similar to the edges. So like having an object and where the shape, where the edge of that object is. It's not immediately that one which is learned in the layer 1, but this is something that, okay, if I go through that edge, I see some difference. That's what is called a gradient. So from outside of the object, I go inside to the object, I see that I have some kind of gradient, some kind of change. And that's what they have seen, that's what the first layer does. Tries to detect these kind of changes, that the changes are which direction happening. In the second layer, the algorithm starts learning the shapes. So like really detecting that what kind of shapes and edges and what we have on the image. So you can see that, for example, where we have that, I don't really know that maybe we have an eye here or many different objects, but the circular shapes are present. Because the algorithm in the second layer could somehow learn that, okay, based on the gradients, I see where the edges are, which is really important because that's one step of understanding that what I see on the image, seeing that where are the border of that specific object. There are other layers. I didn't want to show you all the layers, but at the end, in that case, in that algorithm, there were 5 layers. So the last layer was really the information which was learned or which was extracted for really the classification. So what we see on the left-hand side is the most important shapes and most important part of the image, which leads me to have a good classification. Those are the information which is needed to decide that which class is corresponding to that specific image. So for example, what we see for the dog related images, that we have that 2 pointy ears, which is really important for the classification. So like, I don't know, a mouse doesn't have that kind of pointy ears, or I don't know, a desk doesn't have pointy ears. So if I want to classify something as an animal, and maybe that kind of mammal animals, and maybe as a dog type, then I need that pointy ears. So this is what the fifth layer tried to learn. We see on this segment, so on these 9 images, that the eye is really, really important. So we see that the eyes, let's say it's highlighted in the output. So what the algorithm detected, the most important part of the images is that circular shapes, so having the eyes. And based on that information, the classification could be better. So that's how extraction really works. That originally we had like a bunch of pixels, like many color values, and we don't see, as a human, we interpret that they are connected to each other. So we have so-called spatial information, but the algorithm doesn't know. And the algorithm has an iterative approach to understand that what a shape is, what an edge is, and what is the most important part of the image, which leads to a good classification at the end. So if we can do something like this for an algorithm, that's really nice, because we are more or less suggested that, okay, the algorithm works in a proper way. Because we see that, yeah, really for us, if the class of that image is eye of an animal or something like that, then yes, I have to extract or I have to highlight and just focus on the eye part, and that will be the information which is needed for me, what will be the classification at the end. So it's really nice if we have something like this for image processing. It is really nice if we have tabular data. In that case, we have some tools which we can use for this explainability. But I want to highlight that this explainability could be something which you can think it's a nice to have, not a must to have. But in many areas, this is a must to have. So I'm working with hydrology guys and water management guys, and they are really, yeah, let's say control freak in the sense that they want to understand that how a forecasting algorithm works. So if I want to forecast, for example, the water level at Szeged, then they want to understand that if I have that forecast and if I have many calculations in that black box, which I use as a machine learning algorithm, they want to see that above Szeged, not so far, we have a tributary. So another river meets with the main river. So they want to know and they want to understand, and they want to be sure that because the tributary is really close to Szeged, where I live, that on that tributary, the first station is really important for my forecast, because that's the most affecting one. So I have the main river. From the main river, of course, the station above is really important, because that's where the water comes, hopefully. But if I have a tributary really close to my station, then that other station along that other tributary river should be also important. So if I can show them that, okay, these are really important, and these have really high weight, and these are really important for the algorithm which I use, then they will be a little bit more suggested, and not only just with the performance and the accuracy values, but additionally with this information. I don't think that I have to talk a lot about the clinical decision making, why it is really important for a medical doctor to understand that if that automated algorithm says that, okay, this should be the dose of the medicine, or this is the classification of or the binary decision, or some kind of risk estimation that this person has that kind of disease or that type of disease, the medical doctor should understand or wants to understand that why this is the decision. And for them, somehow this explainability should be enabled. So for them, you can develop the best algorithm on the world, but if you don't enable additionally the explainability beside that algorithm, that they won't believe it. And after a while, they won't just use it. And that's an issue. So we can have the best algorithm, but if they don't understand it and they are not sure that it's working properly in its brain, then they won't use it, even if it's the best algorithm on the world. So those areas, those are just without completion, of course, or the sake of completeness. That's the areas where I'm working. So I have to be a mathematician there. I have to answer for that kind of questions which I could raise. So, having the counterattack from myself, but I really enjoy that, how to figure out these kind of explainability approaches and how to make an algorithm explainable. At the end of the presentation, what I want to collect that, so how many algorithms we have in the industry, so in production, which are AI driven. Just having like an experiment with our thoughts. So one is that it has a long past, let's say. Those are the recommendation systems. So like for Spotify, for Netflix, so for Meta, when somebody is using Facebook, for example, or for Amazon. So those recommendation systems are really in production for a long time. And they are working quite well. But what happens if they don't work well? Nothing much, right? Because something was recommended and I just refuse. And I don't care. So I cannot say that these kind of recommendation systems are so-called safety critical, because these are really nice features and they can get more money, or the subscription fee could be much higher if they have that kind of features in their product. But at the end of the day, if they just cannot figure out the style of music which I like, nobody can, because I like a lot of styles of music. Then not Spotify will be the first who can figure out, because I don't know either. But if they can just recommend me something nice, then it's fine, and I'm really happy. But if they cannot, I'm a little bit sad, but I cannot say that I'm super sad and I won't use Spotify ever. A little bit getting closer to the real panic that robots are attacking us or just stealing our job, right? So that's another huge scandal that, okay, they are really stealing our job and they will just replace us. Yeah, I cannot say that that there are some jobs and there are some areas where a lot of AI assistants could be used instead of the human work, because that's monotonous and not efficient how the process is working. But all in all, if we consider Copilot, which is a programming tool for GitHub, or we consider, for example, the Adobe products where you can generate AI images, and maybe a lot of people here are against the AI-generated stuff, but Adobe is using also AI supported, and it has AI assistants, or SAP, where a lot of bank-related and finance-related and other kind of invoice-related stuff can be handled. And they also have AI assistants, what to do with the data, how to visualize it, how to rearrange it, and so on. So in that cases, of course, programmers are, the good programmers are not afraid that their job will be stolen, which I typically say that if I want to have a good code, then I have to prompt it. So I have to write it down. So the customer should know what it wants or what they want. But the customer don't know, so we are safe until now, because they cannot just specify it quite well, so the code cannot be so good, and I cannot use ChatGPT or Claude or anything else, because at the end of the day, it's still the requirements and that kind of the managing the product it's still something which we have to do. So the programmers, of course, many parts of the programmer job could be replaced or it could be enhanced. I say not replaced, but enhanced with AI, but I cannot say that they will take our job in development. But we have a really good keyword in this part, which is assistance. So this means that we have a human in the loop. That's how it's called, HITL, human in the loop. So this is assistance, so not like replacing. And this is how the production looks like right now. Copilot could do really nice stuff. Gemini CLI could do really nice stuff, but we still need the human in the process. So it's not replacement yet. It's not full automation yet. Some technical readiness level is also reached, but it's not ready. It's not that ready yet. So they won't steal our job yet, because still we have in assistance mode and we need the human in that loop. And also another typical example, the driver assistance systems. So like ACC, adaptive cruise control, or automated braking for the cars, and many other nice features in the cars, which are still driver assistance. So we don't really have the full automation when the car, we just sit into the car and we just open our laptop and we just close it when we reach our destination. So that's not the situation right now. We still need the human in this loop also. We still need in the process. Many manufacturers are really working on driver assistance systems, but all in all, the full automation is not reached yet. And it's really tough. And why it is really tough? Because we have the law. We can have legal issues. So the first really naive idea that I can say that the algorithm is quite accurate. Okay, 99%. The best, chef's kiss. But what happens in that 1%? And what happens if it doesn't work once and it's a self-driving car, it causes an accident, and an accident costs a life? Who will be responsible for that? The algorithm? It's not a legal person, as far as I know right now. The manufacturer, yeah, the manufacturer can say that, okay, it's really highly accurate. Okay, that this comes that, okay, we need like the future CSI when we are really investigating something in the brain of the car. What happened? What it saw? What happened in that specific situation? What was the decision? What was the line of decision? What it made to not braking, but I don't know, accelerating on doing or missing something? What was the situation, and investigating that? So having a new kind of future Sherlock, that figuring out that how the algorithm was thinking. Let's say we don't have explainability, so maybe we don't know how it was working. So this responsibility question is really something which is a hot topic right now. Of course, many other hot topics are related to self-driving cars, for example, cybersecurity, that nobody can hack my car, which is also really a problem which can lead to this kind of responsibility questions. So many other questions are raised to the legal person, the lawyers, how to handle these situations. Another example, that's an urban legend, or maybe it's true, that there was a lady who was drying her cats in the oven, and a surprise, it didn't work. Or it didn't work properly, let's say. And so this is from the internet, of course, that for a new oven's instruction manual, we have a caution message that never attempt to dry a pat in the oven, which is totally fine. So we have an accident. So in the instruction manual, we will write down that don't do that. So that's a known limitation. Okay, this could be funny, but we know that this is a limitation of the oven. Don't dry your pet inside the oven. We can write it down. So legally, if somebody does it, despite the instruction manual says that, okay, you should not do that, then the responsibility will be not mine. But all in all, that's something which is known, a known limitation. But for a self-driving car, when I don't know when it won't work, because the foggy weather will be a limitation. How foggy the weather should be. Or somehow a car in front of me has a dirt which just jumps to my car, jumps to my sensor, and that just screws up my whole perception, and it will just lead to that problem which I didn't know before. So the environment which I have to know, and I have to know the limitations, is really huge dimensional. So I cannot prepare for all the situations. I cannot prepare for all the limitations. I don't know precisely all the limitations. And that's why I need evaluation. That's why I need comprehensive and completion-oriented and multi-scaled and multi-level evaluation algorithms to understand these kind of limitations, to say that, okay, legally this self-driving car is working. Legally, this fully automated medicine dosing algorithm and tool is working. And if I don't know the limitations precisely, then I'm still at the situation that maybe it cannot go to production. I cannot release it. So that's the situation right now, which I wanted to collect without the sake of completion or completeness. So some closing remarks. That won't be a surprise. So we need domain-specific evaluation techniques. So this doesn't mean that if I have some good evaluation techniques for water management, that doesn't mean that I have good ones for medicine. Okay, so all the evaluation techniques and methodology should be domain-specific and detailed. Many areas will need explainability. That will be something which is crucial and the need for them. It's a must, not something which is nice to have. And at the end, we had a philosophical question when I was working on that driver assistant projects, that maybe some lawyers in the future might have a degree in engineering, because that will be the need to properly handle cases related to AI, because they have to understand what happens in the black box. They have to understand these kind of charts and explainability and a lot of things when they are considering a legal issue and a legal case. So that's the future of law, hopefully, that it will get closer a little bit to engineering, and engineers will get a little bit closer to law, to lawyers, which could be really nice. So that's my closing remarks, and with that, I want to thank you for your attention. Thank you for your patience. So like 70 minutes, this is, yeah. You didn't shoot me down.
I was trying to.
Any questions, comments? I think I'm super excited what you think.
Hello, I would have one philosophical question. What is creativity, and is AI creative? So combining new information to create new ideas. The first one, I'm going to have a second one. Maybe I'll say it. But I think that the economy is driven by humans making decisions, and decisions are based on our needs. And then also making the decision, we need to trust the other party, whether we want to order it. And then what is the role in AI? So it is just an assistant, or can you I'm not completely sure, but the first
Okay.
one about the creativity. And
Yeah,
economy.
Yeah, so I'm not a super philosophical guy, but I was thinking a lot about creativity and how I see creativity as a mathematician. So I'm really like a rational guy, is finding relationships between pieces, components, objects, which was not present before. That's how I see. So I'm a little bit graph theoretic approach, but somehow finding these new edges, these new links. Of course, so somebody who is who has a degree in, I don't know, psychology, maybe they have other thinking about that. But as a mathematician, that's how I see creativity in many times. At least sometimes in mathematics, in the research, that finding relationships which were not shown or not existing before. In this sense, AI, if we say that this is creativity or this is one perspective of the creativity, then AI, which is really does that job to find the relationship between data points and data features and aspects and so in this sense, AI could be creative. And that's why I started with that, my relationship with ChatGPT, that this is really close for me to that kind of text generation and prompting something that what could you recommend for this situation. And I just write it down what I want to consider. And ChatGPT gives many different answers and perspective, which I didn't think earlier, and that's how it just gets a piece of information which he thinks it's important and puts it into the sentence, and that's how I would do creative job in that kind of textual generation.
So is it then the role of humans? The AI is in the box; it's all the data that it has taken in. But maybe we have other neurons that
exactly. So how I see that our creativity could be enhanced but not replaced by AI. But enhancement is like emerging, and that's how I see. The other question was about
the economy, and so people have humans have needs, and then they make the decisions whether to buy something. And of course, AI can assist, but it can never replace humans because it doesn't have a need. It's a machine. So, what do you think about the consequences for economy?
Yeah, unfortunately, what I see and how so for example, what I see in Hungary, but I think it's a world phenomenon, for example, in the world of programming, that they don't, the juniors, so the fresh programmers don't get so many jobs, and there are not so many jobs available on the market. In Hungary, that's kind of a situation. So the meteor programmers are the ones which are really...
Which is a huge risk because then people don't learn. And at some point, we don't have experts anymore.
Exactly. So I really, that gap, so this is assistance still in the programming and developing and engineering a good, sustainable, maintainable software and product. So these kind of issues are still present and solved by human. Of course, this is also developing. And the problem, what I see from the economy side, that many junior level, I don't say trivial tasks, but simple tasks, which are the steps to get better and better and better, are done by the AI tools. And the meteor peoples are doing that kind of simple task using AI because they can do that, because that can spare the time, which is really something which is not a good direction. I don't think that this is a good direction, because in that case, the junior developers won't be really trained, so they won't reach that level, then they can use the AI tools in a good way. But maybe it's related to your question in the sense that it's an economical sparing technique to having less people. because that AI doesn't need, so that doesn't have that need, that kind of need that like having that kind of environment, working environment or working place and future development and so you have to take care about less people as a company, which is, I understand it from the economical side, but I don't understand from the perspective of the future of this whole industry in one sense. So that's something which I have analogy or something comes up to my mind. Yeah, but this is really philosophical, yes, that how these AI tools will assist, but more assistance means more time is spared, so less people is needed. So somehow the people should be adapted to this assistance. So some other jobs and some other parts should be taken into consideration instead of what they do currently, which could be fruitful. So this is what I say, enhancement, but this could be interpreted really badly by people who are paying for these people. That's.
I think it's also a threat to democracy and our societies if the people don't develop anymore, or we exclude the younger generation or the juniors, and to be fully part of the society and learning and different aspects and thinking.
And failing also, so yeah, that's part of the process.
Learn by failing, and if it's outsource our humanity to machines, I think this would be a hard leg.
Yeah, I understand your concern. Yes. Yes. Any other question?
Thank you for the talk. I'm curious about your thoughts on AGI, whether it's obtainable, and if not AGI, so
AGI. Okay. I'm not super into the general intelligence. What's the situation right now, and what the current developments are. A lot of focus is going on that LLM technology. That's what I see. I know that the Nobel laureates are still working on. So the three fathers of AI are the Hinton and the other guys are working on that. But I don't really know what's the situation right now. But the last time what I have seen is still this kind of questions, that explainability, so understanding how this is working and how we can connect with that, with the algorithm, because somehow that's something which we have to do. We have to connect with it. We have to connect with the black box. It's still something which they have to solve. I don't know the situation right now. Unfortunately, I'm not this broad in my view, but if anybody knows something about AGI, I'm really open for this discussion. Yeah, so so AGI is the artificial general intelligence, if somebody is not familiar with that. And what I have shown to you is the ANI, so the artificial narrow intelligence. So really task-based and really focusing on the task and solving some problem. So I don't want to diverge from your question, sorry. Just I want to, because that's also, I forgot to mention that, so ChatGPT and GPT is something like for generation. So you can ask that how that kind of parameterization was done. So how a generative algorithm can be trained, how that parameter search can be done. And for LLMs, it's still, it's like, it looks like AGI for me sometimes, the ChatGPT, like this creativity and connecting stuff and creating something new or finding something. But at the end of the day, how the ChatGPT was created was ANI, because the brain of ChatGPT was trained in a way that they given tasks for that brain. So like having the engine of a car and putting into different kind of vehicles and saying that, okay, you should accelerate here, you should brake here, you should do a lot of things. So at the end, the training, so this parameter search was task related and task oriented. But the brain was evolving because many different tasks were shown to that. And at the end, it didn't matter that what's the specific task and what's the accuracy or the performance on the specific task. They just put the brain and used it later. So like what I see that what it looks general intelligence today goes back in the training procedure and a lot of things to the narrow intelligence, because we need tasks today in many situations to train something and to have a better performance on some kind of tool. That's what I can say. I didn't want to dive, sorry, just I wanted to share that also. Yes?
What are your thoughts on quantum computing? How will it affect our current models we have of AI? And how drastic is the change if quantum does happen?
Yeah, so I have just more information about the current state of the quantum computing, how many processors and pieces we have, how many cores we have right now. What I see is, on one hand, it will give space and opportunity for those kind of tools which are slow today. So if I have better units for the computing and that can be faster, then those tools which are slow in the inference, so like generating something or taking a decision. So for a self-driving car, you need only just 50 milliseconds for 1 unit of decision. So in that case, I think the inferential part will speed up. So much more algorithms will be much more efficient and could be built into machines where this quantum technology can be applied. I cannot imagine that in a car there will be a quantum computing unit yet. Hopefully once it will happen, but I cannot imagine it right now. On the other way, so the parameter search could be really time-consuming and memory-consuming and hardware-consuming. So what I can imagine, just from the side of the mathematics and the hardwares, is like it speeds up this kind of computation in the optimization, which was the key for this LLM technology. So when this attention and all this kind of stuff happened, then that was the breakthrough. That was when they said that, okay, we have found something which can work with terabytes of information, which was not possible earlier. So that's how I see, from a really simple researcher and simple guy, how the quantum technology can help us to have better AI tools. If you have better ideas, just share it with me, because I'm really curious about that. Yet. Yes?
Yes, well, I try to make it short. It's difficult for me. But I want to make...
PR2 at least.
I'm doing just science for fun. So my first, I want to make really fast simplifications. And one of those is the relation what I listened about ML and then about GPTs. So actually, to say how I see these GPTs, this is gangster simplification, but the next letter, what you are predicting, is about some kind of Kolmogorov-Gabor polynomial on a higher degree. Mm-hmm. And then this makes the total neural matrix. Mm-hmm. And then you do the regression about that with, for instance, SVD. So you find the most highest predicting modes. Okay. Now, something which I found, of course, is how this seems to develop is that natural languages are very complicated, very informal, and when you speak with natural language about your thoughts, it makes very difficult to predict about how accurate is the language. Mm-hmm. And as we well know, these GPTs are coming from the world of programming. So the more accurate language you use and more formal in your problem, it becomes somehow more predictable. And then another thing which comes very near is about the languages, about the level that languages rises on levels higher and higher and higher on the level of abstraction. So you could, for instance, formal languages like describe with graph, which
automata and so.
And this, and use those to predict your things. And it's quite wonderful when you try to do some semi-formal problem with making a YAML specification. Or then you say that, please make from this problem a YAML specification and then put the GPT to do and make those. And then to compute those results, finding out papers, and then they compute back to those results which I have, and they do, because one of the problems is this catastrophical memory loss. You come all time that, but when it starts to be able to write like this codex, you can write it on the disk, and then you make these RAG systems which you can make indexes in each directory, and it finds back the essential abstractions and finds out. So you don't need to do this. What are they called? This vector. I'm not very well known.
Embeddings. No.
Yes, vector embeddings. With just this ordinary, old-fashioned, like reader would do. I mean, using cars in the old-fashioned way. But this is something which do you use these kind of methods that you make code with or approach ML with that approach?
No, I don't use that once. I have just sparse information about what they try to do to replace the representations. So like Kolmogorov neural networks, I read them once, that how to replace the artificial neural networks, and just really having a little bit more deterministic and having like going back to a polynomial problem. And also what I see that they are working on, understand how this representation could be improved inside, because that could lead to less memory, that could lead to better performance, or that better performance, we can say. I don't work with them because what I do is, which I didn't tell about, that in Hungary, the hydrology, so this water management area, is really data rich. So having a lot of data, because sensors are just creating the data day by day, but really insight poor in that sense that the data-driven algorithms are not really introduced in the operative use. So we are really in the beginning, and I didn't try GPT in the very first, or transformer. So we did a try with the so-called temporal fusion transformer, which is a really big architecture for time series forecasting. But we realized that the transformer technology and this whole GPT technology is really for huge data. But for us in Hungary, that amount of data is not that huge. And this is not so real time that we cannot use a recurrent network, which is slower, and it's slower to train, but at the end it can lead to better performance than a transformer, which is really based on the simplest bricks and try to enhance it towards this sequential modeling. So I didn't work, and I don't see that whether I can work with these kind of technologies which are really going to the peak, that how to change the architecture itself a little bit, because that's what you mentioned. For me is like how to, or the framework, changing the framework or replacing the framework to be more efficient maybe, or having a totally different idea. But so I can resonate with that ideas which you mentioned.
Okay. Well, just my thoughts is it seems like this culture would change things finally to Python code and humans to robots. I'm sorry to say, but it will make the world very mechanistic. This is my feeling, and I'm doing it.
Okay. I think the director said that it's like we are out of time. Sorry that I was 70 minutes of that time. So thank you for your attention again, and thank you for your patience, and thank you for your questions and answers. And have a really good evening.
And thank you for excellent lecture.
Thank you.
Excellent understanding.